We've introduced the Jacobian, so let's talk a little bit about its explicit definition. So when we're dealing with double integrals, what we call the Jacobian, JUV, is defined specifically in terms of these x, y, u, and v functions. So if I could say x equals some explicit function of u and v, and y is some explicit function of u and v, then the Jacobian, this JUV, which also has this notation, this partial, it looks like a partial derivative, but notice that you actually have multiple variables in that partial derivative notation. I don't really like that notation, but I get why people do it. Is equal to this. So I have the partials with respect to x across the top, and the partials the partials of x across the top, the partials of y across the bottom, the partials with respect to u across the first column, the partials with respect to v across the second column. So x, x, u, u. And you just walk along that. So what you do here is take the determinant. So this is actually a determinant of a matrix. And if you remember how to take the determinant of a matrix, for a 2x2 at least, what you have is you kind of go across, multiply top left by bottom right, and then you subtract bottom right or top right by bottom left. And so you end up with this expression, dx du dy dv minus partial of x with respect to v times partial of y with respect to u. And that's the idea behind this. So let's go ahead and compute an explicit one for something that we're very familiar with, polar coordinates. So we've already used polar coordinates when we did coordinate transforms, and we talked about how we got there, right? We came up with a little bit of a sector, and we said, okay, well, r goes this along, and you have this delta r and a delta theta and all that. But the Jacobian provides a very, very nice and clean way to derive how that happens without having to sketch out a big, large piece. All I have to do is define x as a function of r and theta, and y as a function of r and theta, and then I can run the formula and I can get the change of variables. So let's run this here. So if I'm doing j r theta, well then to do that, what I need is the derivative of a partial of x with respect to the first variable, which in this case is r, the partial of x with respect to the second variable, which is theta, the partial of y with respect to r, and the partial of y with respect to theta. So I need to compute these partial derivatives before I take this determinant. So if I compute the partial derivatives, the partial of x with respect to r, well, this is constant, derivative of r is 1, so it is cosine of theta. Now the partial of x with respect to theta, this is constant. The derivative of cosine is negative sine. So we have negative r sine of theta. Partial of y with respect to r, this is constant. Partial of r is 1. So this is sine theta. Partial with respect to the theta of y, this is constant. The derivative of sine of theta is cosine theta. So we have r cosine theta. So when we take this determinant here, we end up with r cosine theta squared minus negative r sine squared theta, which is r cosine squared theta plus r sine squared theta. And if we factor an r out, we get r cosine squared theta plus sine squared theta, which we know is the Pythagorean identity, so we know we just are. And that makes sense because if we go to the formula, we have this region can be set up for whatever new region, right? We end up with new bounds when we're doing when we're doing that transformation. So we didn't have any bounds here, so we're just going to use the generic S, and we had f of r cosine theta, r sine theta, and remember we have the Jacobian term, which in this case is r, and then you have the new variables of integration, dr d theta. So what we end up with is a way to get r dr d theta without actually having to do any sort of, having to think really hard about it or where that comes from or anything like that. And this is really powerful because not only can we do this in 2 variables, we can actually do this in 3 variables. So if we wanted to do this for a triple integral, which really isn't what we're going to be talking about here, but if we wanted to do a triple integral of, let's say we wanted to do like a spherical coordinate. We said, x is rho sine phi cosine theta, y is rho sine phi sine theta, and z is rho cosine phi. And then we could, our Jacobian for rho phi and theta then is now a determinant of the partial of x with respect to rho, the partial of x with respect to phi, the partial of x with respect to theta, partial of y with respect to phi, partial of y with respect to rho phi, partial of y with respect to theta, partial of z with respect to rho, partial of z with respect to phi, and partial of z with respect to theta. And now we have a 3x3 determinant, and if you've taken linear algebra, or even, maybe it's been a while back, you can remember how to take a 3x3 determinant. And what you'll find is when you get this Jacobian, you'll end up with, I believe it's rho squared sine phi. And so by doing that, we find a way to deterministically do all of this stuff that we might want to do for changes of variables. And we do this for the same reason we do any kind of change of variables. We do it for convenience. A lot of what we might do in this course is practice, and it may not feel convenient, but the idea is teaching us these techniques so that when we do end up with regions that make more sense to describe with polar coordinates, or with cylindrical coordinates, or with spherical coordinates, or even all kinds of arbitrary coordinate systems, we can do that instead of having to slice the regions in all these inconvenient ways beforehand.